So up to now, we've kind of ignored friction in a lot of our calculations, right? Because whenever I drew things, we would just sort of go Fg, Fn, a falling object, things in an elevator, right? So what we have to think about is, well, what happens if there is friction? All right, and so we have to include that in some of our calculations, right? So first we want to know, well, what is friction? And friction is a force, first and foremost, okay? And it opposes motion, okay? So that's what it does. It resists motion. So friction is a force that opposes motion. The symbol for friction is F for the force, and then sub F for friction. And of course, the units are in newtons because it's a force. So that's the units, okay? So why is there friction? Well, you have friction because there's microscopic imperfections between surfaces, and also there are intermolecular forces between surfaces. So let's attack each one and see what it means. So let's start with microscopic imperfections. So imagine these two blocks, and they're sort of sliding against each other. So one's going this way to the left, one's going to the right. And if we take a closer look at the sort of between the surfaces, you see the surfaces aren't exactly smooth. There's little ridges. And so what happens is these ridges are what we call imperfections in the surface. And what this does is what happens is they catch as you're sliding. And so that slows it down. It makes it harder. Okay, so that's your microscopic imperfections. What do we mean by intermolecular forces? So if you think about intermolecular forces, we know that molecules have charges. Okay, so you learned last year, for example, I'll use sodium chloride as the simplest one already. Okay, sodium chloride, it'll have a positive and negative charge, and that's what holds these two things together. But that positive negative charge isn't necessarily evenly distributed. So for example, if you think about water, which is H2O, here's your oxygen, okay, and there's your hydrogen. And so what happens is, so that's hydrogen, that's oxygen. What happens is it turns out that the hydrogens are more negative and oxygens are more positive. And so what happens is when I have another water molecule, this side, the oxygen side here, it will want to sort of attract to the negative side. And that's why water kind of clings together. So this is actually what creates the surface tension in water. All right? So these forces are always present. So if you imagine that, there's some charges in the wood here and some charges in the metal ions here, and what happens is they tend to stick together a little bit. And these intermolecular forces, they create, friction as well. Right? So you can never eliminate friction. You can make this as smooth as possible to get rid of these imperfections. You would still have intermolecular force. This is why friction is present. So as I said before, friction opposes motion and is only present when an object is moving or about to move. And I'll explain what I mean by about to move in a minute. The force of friction depends on two things: the nature of the surfaces and the normal force, which is sort of how hard the surfaces are pressed together. The nature of the surface is called the coefficient of friction. And we'll look more at that in just a minute. that tells you how sticky the surfaces are. So every two surfaces, they will have different coefficients of friction. Okay? Now, there are two types of friction. One is called kinetic friction, and one is called static friction. And if you can see from here, it says kinetic friction is the friction of moving objects. Static friction is the friction in stationary objects about to move. So let me explain that with a video. Okay, so we take a look right now, and we notice that this hole punch here is not moving. So if it's not moving, there's no friction between, okay, right here, the bottom of this, and the surface of the table. No friction at all. There has to be some motion or about to have motion. So if I take a look at my lanyard, there's no slack here now. When I pull it tight, now it's tense, it's taut. Okay, so now there's no slack. Now, normally, if this surface here was frictionless, this hole punch would move. It's not moving because of static friction. That's what's holding it in place. And then if I apply a little bit more, okay, force, now the hole punch is moving, which means that there's now kinetic friction. So here there's no friction. Here there's static friction holding it in place. And now here there's kinetic friction. So as you can see from the video, with kinetic friction, it resists motion of moving objects. So when the hole punch was moving along the desk, whereas static friction resists motion of stationary objects about to move. And this part is important, right? Those objects are just about to move, they just haven't moved yet. If the objects aren't moving at all, there's no friction. Now, if there's two types of friction, that means that there's two types of coefficients of friction. And as I said, coefficients of friction, they describe the surfaces in contact. That's what their job is. And if two surfaces are really sticky, then they'll have a high coefficient of friction. And if they're not so sticky, they'll have a low coefficient of friction. All right, so that's why it says it describes the stickiness between the surfaces. It's important to remember coefficient of friction. It is not equal to the force of friction. Right? This just tells you how sticky the surface is. Coefficient of friction just tells you how sticky the surface is. Force of friction is how hard you have to push or pull to overcome friction. Now, obviously, if it's more sticky, you're going to have to pull harder, but there's more to it than just that. All right, so it's important that you know the difference. The symbol for coefficient of friction is the Greek letter mu, okay? And it looks like a cross between an M and a U, and that's why it's called mu, okay? So that's the symbol. It's a Greek letter again, so there's another Greek letter for you. So that's the symbol, and it has no unit. So it's what we call a unitless symbol, or a unitless physical quantity. So here are some examples of coefficients of friction. So if you take wood on wood, notice there has to be two surfaces, right? In order to get friction, one thing has to rub on the other. So if I have wood on wood, the static friction is 0.4, and the symbol would be mu s, and the kinetic coefficient of friction, mu k, is 0.2. You notice that the static friction is higher than the kinetic coefficient of friction. Okay, so this is higher, this is lower. Why? Well, it's always harder to start something moving than to keep it moving. If you look at ice, you notice that the static friction for ice is much lower than wood. Of course, when you slide ice on ice, it's much easier than if you're sliding wood on wood. And the kinetic coefficient is even lower. What if I slide metal on metal? Well, if it's metal on metal with no oil, it's very high. Have you ever tried to rub metal against metal? That's going to be hard. It's even harder than wood on wood. But once I lubricate it, in other words, I put some oil or something on it, suddenly it slides much easier, which is why you have to have car or engine oil. Okay, so these are just some examples. A couple of things that we notice, though, is that, number one, mu s is always bigger than mu k, okay, since it's harder to start something moving than keep it moving. Okay, it is then, sorry. The lower the coefficient of friction, the lower the force of friction. Okay, in other words, easier to move. Okay, so rubber on dry concrete here is really hard to move. Try and push a car. Okay, rubber on wet concrete will be easier, which is why it's easier to skid when you're in rain than it is on a dry day. Right? This is the exact reason why. So let's try an example of how we would use friction. The first thing we do before we do that is let's figure out what mu is. So mu is a ratio between the force of friction and the normal force. That's what mu is. Okay, and so what that means is that if we're looking at the coefficient of friction, this unit is in newtons, this unit is in newtons, and the units cancel, and therefore mu is unitless. So that's why it has a unitless quantity. But that's what mu represents. That's how they sort of defined mu. You could think of this as a definition for mu. Okay, so the definition for the coefficient of friction is the force of friction divided by the normal force. Now, scientists, they like to rearrange that so that they say force of friction is equal to mu Fn. And this is actually a formula to calculate force of friction. So if we take a look at this example, we have a wooden block of mass 25 kilograms pushed across a wooden surface. The question is, what is the force of friction acting on the block? So for A, we are just looking for it just before it starts to move. So we're going to need to know the kinetic coefficient of friction, static friction. So let's look up, what do we get for static wood on wood? It's 0.4. So we come back down here, and we know mu s is 0.4. Okay, we know the mass of the block is 25 kilograms. Right, so now what we have to do is we say, well, how do I find the force of friction? So let's draw a free body diagram of the block and see what forces are in action here. So if I take a look, of course, it's being pushed, so there must be some kind of applied force. There's going to be a force of friction acting in the opposite direction. It's on Earth, so we're going to have gravity. And it's sitting on a surface, so there's going to be a normal force. Now, if I take a look at this, the normal force and the force of gravity are balanced out. How do I know? Because the block isn't moving vertically at all. There's no motion up and down. So what that means is these two forces cancel out. In other words, the normal force is equal to the force of gravity, except in the opposite direction. Okay? So if I want to find the force of friction, we've just learned our new equation, it's mu Fn. I know mu, and now I know Fn because it's actually equal to Fg. So that's going to be mu Fg, and from our equation from our last lesson, that's going to be mg. So that's going to be 0.4 times the mass, which is 25, times 9.8. And that gives me 98 newtons. And therefore, after significant digits, 2 sigs, 1 sig, so it's one significant digit. So that should be the force of friction is equal to 1 times 10 to the 2 newtons. So 100 newtons to one significant digit. I guess you could write 100 if you wanted. So 100 newtons, that's also one significant digit. Okay, you should be able to do B on your own, and you would get, hopefully, 50 newtons, and that's for B. So you guys try that on your own and see if you get that answer. Okay, let's take a look at this question. In this question, a 52 kilogram student is sitting on a rolling chair. The teacher pushes the student with a force of 620 newtons. If the coefficient of friction between the chair and the floor is 0.25 newtons, what's the acceleration of the student? So there are quite a few things happening here. So always, let's draw a free body diagram of the student. Okay, and I know it's a student because that's what I'm looking for, the acceleration of the student. Right, so if this is the student, okay, sitting here, and what forces are acting on the student? Well, obviously there's gravity and the force of the chair pushing up. Okay? The student is pushed by the teacher, so there's a force applied, and there's going to be a force of friction acting on the student. So these are all the forces that are there. Now, once again, because the student, there's no vertical motion. So this vertical motion, there isn't any. So that means, so therefore, Fn and Fg equal each other. So I can cross these out. Those two are balanced. What's left to find net force, what's left is the force applied and the force of friction. So I'm going to make this side positive and this side negative, and therefore the net force is the force applied minus the force of friction. Now we don't know what these are yet, but I do know that the net force is going to equal, those two subtracted together. All right, so let's figure out what we know. So we know mass, that's 52 kilograms. We know that the force applied is 620 newtons. We know the kinetic coefficient of friction is 0.25, and we're looking for acceleration. So let's plug stuff in and see what we have. Well, F net is equal to ma, F applied is 620, and the force of friction is equal to mu Fn. Well, we know mass is 52. We don't know acceleration yet. That's 620 minus mu is 0.25. Fn, we said, was equal to Fg, so that's equal to mg. So again, 52a equals 620 minus 0.25 times 52 times 9.8. So that's 52a equals 620 minus, so 0.25 times 52 times 9.8 is 127.4. We should have one extra significant digit, so 127. 52a equals 620 minus 127, which is 493. So A is equal to 493 divided by 52, which is 9.48, and therefore A is equal to 9.5 meters per second squared. And so we found what we're looking for. The student is accelerating at a rate of 9.5 meters per second squared. All right, so we'll stop here today, and I'll see you guys in our next video.